We're in the 8th week. This is saying the midterm says it's for week 17, although it's for week class session.
Okay, so the first question, since most of people are already here, I'm going to ask when should we have the midterm? So when I originally planned that have midterm next week, but my question is that can we have it today?
No.
No, please no.
Okay, that's kidding. The thing is like this. So can we postpone it to the end of this month?
Fine with me.
Huh? Yeah, the midterm to the last week of this month.
You don't need to postpone the midterm, just postpone the homework for like 2
No.
days.
I want to, the reason is like this. So I want you to finish your homework. I can answer the question in the homework. So you have a better idea about the knowledge, and then we have midterm. Okay, that's one reason, because I find the homework has some overlap. The other thing is, because the last week of this month I need to attend a DARPA meeting. I will be away. So I think instead of we have midterm, then you don't have class. And then I have to skip away and ask somebody else to teach the class. I think most of you guys still prefer to me to give the class. Anyway, so that's the reason I want to postpone the homework to the midterm to the last week of this month. So I can go for a meeting and you do your midterm. Make sense? Okay. Anybody do not like this idea, please raise your hand.
I have a question.
Yeah, go ahead.
How long do we have the midterm for? How long is it?
I will announce the midterm. I give you about, okay, I will announce that on Tuesday. Okay, on Tuesday. And then you should give it back to me on Friday. Okay, that means you have 3-day window on. He told me that, asked me to do it. So you have 3-day window to finish midterm. And then you can pick up 3 hours in any time during this window, okay? But only 3 hours, okay? You can from midnight to 3 o'clock a.m., probably from 7 p.m. to 10 p.m. It's up to you, okay? But you only have 3 hours, okay? Questions, comments? And okay, so
Just real quick, can I clarify? So you're saying to take home over those 3 days, we're going to take the entire test in a 3-hour block?
yeah,
Cool.
okay. So then, okay, the answer. Online students, check the footage of the video, okay? If you have any other questions, please drop me a message, okay? Answer. What's the last Thursday? I think it's the 27 or 27 or 26, right?
Last Thursday is the 30th. The informal.
Yeah, 30th.
Hold on a second.
The last day is the 30th, the last Thursday.
No. Last Thursday?
Yeah, the
Okay.
last Thursday is the 30th.
So then we have the 28th, right? Okay, so midterm will be announced on November 28th. Okay?
October or November?
Oh. Sorry. I will postpone for 2 weeks, okay? And then you deadline for submission. Was it Friday?
The 30th. No, that's 30th.
30th?
On Halloween?
This Friday's Halloween.
Oh, Friday, Halloween?
Friday's Halloween.
Friday, Halloween. Yeah, you can submit on Halloween, that's fine. I don't mind doing your Okay. Does that work? I will announce on Monday.
Close Wednesday.
And return it back on. You just told me Friday is Halloween, right? You just turn it back on. 29th is what? Wednesday or Thursday?
29th Wednesday.
Then probably just Wednesday, okay?
Monday to Wednesday.
Then that takes it down to 2 days.
What's that?
But that takes it down to 2 days instead of 3 we had before.
You can make it due on Halloween.
And then we're
Now, I don't want to make the make my midterm like a ghost in front of.
What about announce the 27th and do the 30th?
Yep.
Yeah, make it, yeah.
That's fine, that's fine. Okay, so you will have 3 hours to finish. Okay, I will put the instruction on the paperwork. Okay, clear? Everybody online see that? Questions, comments?
Can you make the homework like 2 days after October 17th?
October 17th.
Like
Because October 17th is the qualification exam. And you made the homework due the same day the exam is.
I give it 2 weeks, right? So you should have enough time to finish it.
But we procrastinate.
Huh?
We procrastinate.
When did I put it? 17th, right?
Yeah.
I can give him 19th, that's fine. Before Monday, okay?
that would be really helpful.
You should be give me the good evaluation for my teacher. That's a trick. Make a deal?
Yes.
Deal.
Okay, good. If I find bad evaluation by teaching, I will come to everybody's lab and talk with your supervisor to keep bothering you until the grading. Anyway, let's go back, okay? Come back. So last time we talked about the mixture of ideal gas, right? We introduced the concept of partial pressure, and we also mentioned that the chemical potential of each component only depends on its partial pressure, right, and the T, right? Because all components share the same T, okay? It's not depends on the total pressure, okay? It's only depends on the partial pressure for the ideal gas. Okay, that means if you put different gas inside that tank in the container, it doesn't change the chemical potential of partial pressure of it, okay? That's for the ideal gas case, okay? The other thing is that in the equilibrium, the chemical potential is always the same. So that's the reason we explain the phenomenon of what is called the cosmotic pressure.
Osmotic.
How
Osmotic.
Cosmotic means universe, right?
Yes.
You know, previously I worked in the Department of Physics and Astronomy, okay? So that if I make this kind of stupid mistake, it's just because they ruin my brain. So. That's the reason I escape from it. You know, everybody in front of me in the office, oh, let's see the star, let's see the sun, the flares. I mean, oh, we see the outside particle. Oh, come on, what are you talking about? I have no idea. I need to escape from this place. Okay? And everybody taught me the particles, the quark, I mean, the accelerators, whatever. Oh, what am I doing? Forget about it, okay? Awesome. Anyway, you know what I'm talking, right? So that means that if you have a kind of like this container, we have the partial transparent, I mean the fume. So on both ends, the same kind of gas or liquid share the same partial pressure or chemical potential. Okay. This will be on your midterm exam. All right, probably one last question. Okay, but today in the class, I want to talk about some about the. We will spend about 40 minutes to talk about the behavior of actual gas, okay? And then I'm going to use the rest of the time to answer some questions in the homework. Okay, so that is briefly talking about the mixture of ideal gas, okay? But for most of the case, the partial pressure, I mean, we call it the Dalton partial pressure law of partial pressure. Doesn't hold precisely, but as good, it can be a good approximation, okay? It can be a good approximation. But on the other hand, when two phases or two separate parts have reached the thermodynamic equilibrium, the chemical potential always the same, okay? Always the same. Because this is not derived from the equivalent of the partial potential. Instead, it comes from the equivalent of the Gibbs spring energy. Okay. All right. So today we're going to talk about something. We will continue the topic. Okay. We're going to talk about the behavior of actual gas. Okay. I want to bring a demonstration in the class, but that makes my class more like an undergraduate class. So the reality is I didn't find the setup. But anyway, I have no idea. Have you ever played with the lighter? So we have some gas inside of it, right? What other gas was that? Propane or something? Not propane. Huh? Something like that. Have you played with that before? You see it's a liquid, right? And when you press it, it evaporates, right? Have you ever tried to put that in a syringe and press it? When you go back home, you can try to. I want to bring that one, but unfortunately, I don't have that one gas with me. I need to go to the Home Depot, but I'm so lazy. Anyway, so you know that is kind of gas, okay? What's the name of the gas? It's not propane. What is that?
Butane.
Huh?
Butane.
How do you spell it?
B-U-T-A.
Oh,
C4.
B-U-T-A.
N-N-E. Yep.
What's the meaning of Bu?
It's
Butyl, it's like 4 carbons.
4 carbons. 1, 2, 3, 4. Something like this.
Yeah.
Right? We're talking about some chemical. Anyway. Okay, it's something like this. Okay? We have this structure. If you have chance, go back home. Do this experiment. If you have the cylinder, the syringe, whatever, you filled with this kind of gas inside. Okay? It's gas, right? You press the piston, what will happen? No, it doesn't explode. It's liquefied. It's liquefied. Okay? In the room temperature, you can try to do that. Or you can try to go back home, try to take some gas away from your AC, the Freon. Okay? Use the syringe, press it, become liquid. Okay? So that means, but you know that for the ideal gas, this kind of phase transformation doesn't happen, right? Basically, for the ideal gas, you compress it, it's still gas. Okay, just like you compress the oxygen, nitrogen at room temperature, it doesn't liquefy, right? But for this one, for the butane, you can liquefy it, right? Freon, you can liquefy it. So that means we start to find this kind of the phase transition. But how this kind of phase transition happens? In other words, why the behavior of this kind of gas deviates from the ideal gas? Okay, we know for the ideal gas. We know that for the ideal gas, this is the V, this is the P. Okay, so if we compress, that means we make the V smaller, then the pressure goes up or goes down. Go up, right? Something like this. Correct? The relationship is PV equals to nRT. Right? At a constant T, just like P proportional 1 over V. Correct, everybody? That means the P is the reverse proportional to V. Right? That's the ideal gas. So if the temperature going down, the curve looks like this. Right? This curve looks like this. This is the ideal gas. Correct, everybody? But for the actual gas, this is for the ideal gas. Okay? But for the actual gas, V. At high temperature, yes, it's more like an ideal gas. But when the temperature is low, if we compress the gas, we find that the pressure goes up, of course, right? And then at some point, it starts to liquefy. Okay? And then in this kind of cylinder, you will find that you have more and more liquid accumulate on the bottom. On the top is vapor, on the bottom is liquid. Okay? Give me a second. Let me see whether I can log into the YouTube and find some video. I should bring that one too, but honestly, I have some concern about it because I'm worrying that I just set this classroom on fire.
The more fire, the better your review.
Seriously?
Yeah. This professor had a lot of wow factor in his lectures.
You know that you guys see too much of this kind of cartoon. You know that I'm not the crazy guy. What's the name of that kind of the cartoon? It's the animation. It's called Rick and.
Rick and Morty.
Rick and Morty?
Yeah. Rick and Morty. Yeah. Anyway, so let's wait for the computer to start up. Anyway, so then if we start at a certain temperature, if you keep pressing it, you will start to see the liquid start to show up on the bottom of it. And at that point, if you keep compress, more and more liquid will appear and less gas. Okay. But on the other hand, although the volume going down, the pressure doesn't change. Okay. Then it starts to have this kind of phenomenon. So it's just the flat, okay, just flat, okay. In other words, we already discussed the phase transformation, right? Correct. This is what? This is the this is P. This is the T, right? And we're saying that the hold on. We're going to talk about the which one is P? Which one is T? Anyway, doesn't matter. Let's see that this one is this one is P, this one is T. So we know that we have phase transformation, okay? For example, on top is the gas phase, on the bottom is the liquid phase. That's fine. And then this is if you keep compressed at this constant temperature, you start to have this phase transformation, right? The liquid. I think it's wrong. This is gas phase. This is liquid phase. If you compress the gas phase to the liquid phase, the liquid phase, right? But this is the phase transformation point, right? And if you keep compressing, the pressure doesn't change, okay? And then after all the gas got liquefied, it just becomes a whole tank of liquid, right? If we keep compressing, the pressure of course goes up, right? And then if we further lowering down the pressure, the temperature, we have to start to show something like this, okay? And in this area, it's a mixture of the liquid and gas. Correct, everybody? So this one is gas phase, this is liquid phase, and in the middle is the mixture. Okay? And of course, we can find a curve looks like this, okay? And it shows up here. Okay? It shows up here. This we call is the critical point, okay? That means this is a critical temperature. That means above the critical temperature, we cannot liquefy the gas. And below it, we start to see this kind of liquid and the gas mixture, okay? And we have this area, okay? This area is the liquid plus the gas, okay? Liquid plus gas. So this is the actual, this is the behavior of the actual gas, okay? And for most of gas, the same thing, okay? Although we cannot compress the oxygen, we cannot liquefy the oxygen at room temperature. This is because the room temperature is so high for the oxygen. Okay, if we cool it down and you compress it, it will become liquid. Okay, it will be liquefied. Got my points? Let me see whether we can see the demonstration online. We just go to YouTube. YouTube is a good resource. liquefy of let me see whether somebody show this experiment. I cannot guarantee. I really like this guy, by the way. In a syringe. Yeah, this one is, oh, why there's, the university should pay YouTube to get rid of this kind of advertisement. You know that I should not, okay, see that one? See, I compress, and the liquid shows up, right? Not very clear, but you can see some liquid shows up, right? Can you see that in the syringe? Right? If you keep compressing, the liquid shows up. If you release it, disappear. Let me see whether we have a better demonstration. But anyway, so you know what I'm talking, right? So you're just, kind of instruction. Anyway, so just find the syringe and then put some butane or butane inside. You can try, okay? Anyway, so we don't spend too much time on. As we compress it, it becomes liquid. Then the question is, this kind of behavior cannot be predicted by the ideal gas, right? For the ideal gas, if we keep the temperature lower and lower, we don't have something similar to that, right? What's the reason for that? The reason is the ideal gas simplify the gas, the actual gas too much. Okay, we need to consider, we need to add more factors, okay, in the model. We need to consider two factors. Okay? The first thing for the ideal gas, okay? For the ideal gas, the first thing is we ignore the interactions, okay? Among molecules. The second thing is we ignore the volume of molecules, okay? So we have two approximations. Definitely we have more approximation, okay? But these are two most important ones, okay? These are two most important ones. So in order to consider the actual gas, first of all, we need to fix these two approximations, right? The first of all, we need to consider interaction among molecules. The other thing, we need to consider the volume of molecules, okay? Remember, for the ideal gas, we have PV equals to nRT, right? And V is the total volume of the gas, correct, everybody? But if we consider actual gas, we need to remove the volume of the particles, right? That is incompressible, right? We cannot change the volume of the particle, right? We need to remove that part. Correct, everybody? The molecule we cannot compress. Of course, you still can compress the molecule, okay? That's trigger a chemical reaction, okay? Or the fusion, okay? But that's so far away from what we're talking about, okay? Then we do have to make some modification to the V, okay? So we know that we do not want to make the system so complicated. For example, we know the gas can look like this. We know the gas can look like this, okay? We know the gas can look like this. So a different shape, different configuration, so complicated, okay? Don't worry. Can you draw some more complicated structures? We just make the job simple, okay? Every molecule is just a single bond. Okay, anyway, this is a bond, okay? And then we have another one, okay? So when there are two, we're talking about the volume. We're talking about the volume of each bond taking place, okay? Think about it. When two molecules keep in touch to each other, we cannot further compress it, right? That means effectively, every molecule occupy that much space, right? Because we cannot further move, right? Although the core of the molecule is only that much, but actually it's occupied that much space, right? Because you cannot make the other molecule even closer to it, right? So the volume of this kind of space, this is 2R, right? The volume is what? 4,3 pi 2R cubic, right? That's the volume. Effective volume of each molecule, right? And then the total volume is just times the F-Gallo constant times the Moore number, right? However, you know that when we count this volume, we also, consider this one also have something like this, right? Also, they have some overlap, correct? So the sum on this one actually consider this volume for twice, right? In order to get rid of this kind of effect factor, we just times 1/2, right? Remove the double count. Okay, this is just approximation, don't worry too much. You will find that actually this parameter doesn't, not very critical, okay? But anyway, so in that sense, we can make some modification. P times V minus the N and the molar volume of the atom, the molar volume of the molecule. Okay, that is incompressible volume. That's the volume of the physical volume of the molecule inside the gas. Okay, so we remove their impact. Okay, remove their impact, and only this part can be compressed or expanded. Okay, you don't think? But this part cannot be compressed. All right, pressure. Okay, so we know that the volume, by adding this term, actually we fix this issue, right? What about interaction among molecules? It makes the job very complicated, right? Because we don't know what's the different molecules have different kind of interactions, right? You know that for this kind of the hydrogen, nitrogen, silicon dioxide, not silicon dioxide, carbon dioxide, their interaction basically the van der Waals interaction, right? Van der Waals interaction, basically dipole to dipole interaction. But for water, it's different, right? We have a hydrogen bomb inside, right? That's the reason inside the group you can see that this is water at the room temperature, it's liquid, right? But what about this one? This is gas, right? This is also gas, right? But why this one is liquid at room temperature? This is because you have the hydrogen. You know what is hydrogen bomb? The hydrogen bomb, because you know that the hydrogen basically is just a naked proton, right? And oxygen has the lone pair electron here. So it's a very charged negative, and the hydrogen is very charged positive. Then it can attract the lone pair electron from the oxygen and form this kind of called hydrogen bomb. Okay? It's not very strong, but stronger than van der Waals interaction. That's the reason in the room temperature is liquid. Okay? So if I'm wrong, make some mistake in explanation, please pardon me, okay, because I'm not an expert in chemical. But anyway, that's the reason, okay? But I still do not remember why this one smells really good. This one smells really good, but this one doesn't have any smell. Have you ever smelled this before?
Yes.
How? Got some rotten egg?
Chemistry lab.
Huh?
Chemistry lab.
Chemistry lab. Then you need to sue the supervisor or professor. I mean, they release the toxic gas to the room. Go to the Yellowstone National Park. You will smell it. Okay? Anyway, so then what about this one? How can we build? The model still we don't want to deal with this very complicated configuration. We just want to fabricate or establish a simple model. Okay? Then we do not consider the details of interaction. Instead, we just we call it assembly model. Okay? We just ignore the details. So think about it. If we have a tank of gas, if you have a tank of gas. Okay? We have the molecules inside. And then we just add a virtual plane. We just add a virtual plane. It not necessarily exists, okay? We just have the virtual plane. Separate these gases to two parts, okay? Then, across this plane, this gas will have some attractive interaction. Why attractive? Because for most of the interaction are attractive. One of us interaction with the dipole-dipole interaction or hydrogen bond interaction, they are attractive interaction. Okay? And most of the gas have this behavior. And this interaction is even stronger for the liquid. And this interaction is the surface tension. Okay? The reason you have surface tension is because molecules just attract each other. Okay? We have something like this. Okay, we have something like this. So on the across this virtual plane, the gas on this end will drag this gas to this direction, and the same thing to here. Okay, so basically we have some interaction on the interface. Okay, basically similar to surface tension. So what's the value of it? So basically it's just like the interaction, attractive interaction. Okay, so still remember what the gravity looks like. What the gravity looks like. Gravitational interaction, what's the equation looks like? Is it G times M divided by R squared, right?
Yes.
Okay, so it depends on the mass of this object. It also depends on the mass of this object. Okay? The same thing here. Okay, the same thing here. So it depends on the density of this gas. It also depends on the density of this gas. Okay? But you know the density is the same. Okay, what's the density? The density is the number of mole, is the N divided by V. That's the density, right? But it depends on density on this top, and also depends on density on this top. So it's just a square. Okay? That's a square. Okay? And then that is attractive interaction. We only know that the attractive interaction, no, forget about it. The attractive interaction equals to this one. Okay, I really hate AI, so forget about it. We just add it here, okay? So basically, but it's positive or negative? It's positive, okay? Because it just makes the gas have the tend to be compressed more, okay? So we just add this term. So we have a constant is N divided by A squared and V minus Vm. Okay? Still, we do not consider the format of the interaction. Okay, we do not consider the format or the detail of interaction. We only know that they have an attractive interaction. Okay, if the attractive interaction is very weak, then at room temperature, that's a still gas. It's very strong, it becomes liquid. Okay. And then we have this formula. Okay, this is just some amendment to the ideal gas formula. And this term consider the intermolecule interaction. This one consider the limited volume of the molecule. Okay, and this equation we call it the van der Waals. Okay. Okay, van der Waals equation. Okay, you can call it liquid. In text we call van der Waals liquid. In some other text we call van der Waals gas. Doesn't matter. Okay, we just know that this is the equation called the van der Waals equation. Okay. Then, if we plot the PV chart of this equation, how it looks like? Actually, it looks like this. At high temperature, it's very similar to the ideal gas. Okay? Because think about it, at very high temperature, what's the reason for that? At high temperature, the kinetic is very high. We can just ignore this term. All right, at high temperature, right, we can just ignore this term. It's more like the ideal gas. But when the pressure when the temperature going down, the behavior of this curve looks like this. You start have this kind of kink, and then further down. And then Something like this, okay? My drawing is not very accurate, but you know what I'm talking about. We start have this valley. Go ahead.
You'll be in the picture.
Wait, what's the axis?
I think I look better in the picture. What's that?
What are the axes?
Oh, it's just take a picture. I have not got a chance to write it yet. This is the P, this is the V. Oh, I'm sorry. This is the P, this is the V. Okay? And the temperature going up on this direction. Okay? This is the low temperature case. This is the high temperature case. At the high temperature, its behavior, the gas behave like the ideal gas. But when temperature going down, we start to have this one. But this one still looks different from what we're saying, right? Because for the actual gas, the Abbe curve looks like this, right? Right? But it now looks like that. Okay, so then here following, then I'm going to tell you what's the argument. Why this one still work, okay? Why this one still work. Before doing that, I think everybody already knows why it still works, okay? First of all, we know that for any kind of object, as long as it stably exists, the partial P, partial V, always negative, right? That means if you make the volume smaller, the pressure goes up. That's stable, right? Think about the table effect, press it, it's just react, right? It's not like I compress it, it becomes smaller and smaller. I press harder, it's shrinking even more, okay? It's not stable anymore, right? It's not stable anymore, okay? Just like we study, I push you hard, you should devote more effort. It's not like I push you hard, I just give up. I push even harder, you give up more, okay? Then that's hopeless, okay? You have to give you this kind of the compress, and then the pressure going up. That is how the system is stable, right? That means in this area, the system is not stable, right? It's not stable at all. That means it does not naturally exist. Okay, does not naturally exist. But on the other hand, we still can calculate the change of the Gibbs free energy. Okay? Remember, this area is not stable. Okay, we can draw something like this. Okay, this area is not stable. It's not stable. Okay. We know this is unstable area. But we still want to know what happened there, okay? We know this is unstable region. We just plot one curve. Okay, we just plot one curve. We know it looks like this. And this area is unstable. And still remember, what is the driving force for the phase transformation? We mentioned that last chapter. It's the Gibbs free energy, right? The system always has minimize the Gibbs free energy with a constant pressure and constant temperature. Let's see how Gibbs free energy evolved as a function of PMT in this case. Because we know this curve as a constant temperature, right? This is the constant temperature curve, so temperature doesn't change. Then the delta G simply equals to what? V dP, right? This is the change of Gibbs free energy. Correct, everybody? Then it looks a little bit weird because V is here, P there. Then we can just flip. We can just flip the coordinates to see what's going on. We just put this one P, put this one V, okay? And then it looks like something like this. Correct, everybody? Rotate it, okay? So we can calculate the delta G. We can calculate from this one. Let's choose this as the starting point, okay? At this point is the G none, okay? So we can calculate the We just start from random point, okay? And then this integration is just the area underneath this curve, right? The integration, for example, if I integrate from here to here, then the integration is just like the area underneath of this curve, right? This is the integration, correct, everybody? All right, so then we can do the job. We just give several points. Just see this is A, this is the B, this is the C, this is the D, okay, this is E. Okay, F, G, H, I, J, K, L, whatever. Okay, we have several points. Okay, and then we can plot a chart looks like this. Okay, we just calculate the Gibbs free energy as a function of P. This is the P. This is the G. Okay. The A point is here. Okay, we just assume A is here. And then when the pressure goes up, it's going to be the area is positive, right? The area underneath AB curve is positive, right? That means the Gibbs free energy is increased from A to B. Okay, the same thing from B to C, from C to D. It's all just keep increasing, right? Correct, everybody? Go to the E. Let me redo the job. A, C, D, E. Okay, keep increasing. But something changed after the E point. The curve starting from some turn, right? Turn to the left. Correct, everybody? It started to turn to the left. Then the area becomes negative. Correct, everybody? The area below the D, E, and F become negative. Correct? Because because at that moment the V decrease, right? As the P decrease and the V also decrease. I mean, hold on. No, the V is positive, but the V is positive, but delta P become negative, right? On this part, right? So the integration is negative. That means the area under this area, the area under this curve become negative, right? And then you can see the chart start going down. It start to going down. Yeah. Anyway, so it's going down in that way. Actually, it's going down. That looks good. I'll make it more steep. It's going down in that way.
Can you explain why the area becomes negative?
Yeah, because the area becomes negative. Then the Gibbs free energy, the area can become negative, that means Gibbs free energy is going down, right? And also pressure going down. Then the curve start turn at from the curve start to turn the direction from the point, right? And then this is F, G, H, I, okay? And from I point, it's become positive again, right? Something like this. This is I, this is probably J, this one K, this one is L, okay? We have this L version. Looks like this, okay? Okay, so, and we already know between the I and E point, okay? Basically, this is E point, this is I point, right? Simply, the system not stable, right? The system not stable, correct, everybody? The system is not stable, it's not stable. Then we know that this curve, this area actually doesn't exist, right? It doesn't exist, right? Basically, can just see the H, G, F, this area doesn't exist, right? Because this state is not stable. The partial V, partial P is positive, right? Not stable. And this is unstable state. And this part is unstable state, okay? Unstable. Okay. But look at here. For example, here and here. Both parts are stable state. Both parts are allowed state, right? They are allowed. You have partial V, partial P are negative, okay? One part corresponding to this branch. The other part corresponding somewhere here. Corresponding to somewhere here, right? But you can see that, I mean, for example, this part, this half is a CD. CD is where? This is CD, right? This is CD. This is a CD. Okay, this CD, this is C. And then we also have the something like I and J. I and J and J and J and J. Okay, you can see that? CD corresponding to this curve and IJ corresponding to this curve. Okay, IJ is here and the CD is here. Okay, CD is here. IJ is here, CD is here. And you can see that from the Gibbs free energy, we know that the gas actually prefer to stay on CD area, right, instead of the IJ, right? Because the Gibbs free energy is lower here, right? Correct, everybody? That means if I keep compressing, we still go here, right? We're still in CD area, right? And if we keep moving, and then we start to get this point, right? Start keep going, start get this point, right? And then it suddenly, then if we want to minimize the Gibbs free energy, the curve should not go to this branch anymore. It should suddenly change to this branch. Right? That means we go here, and then it start to go to this branch. Right? It start to go to this branch. That means we keep moving. We go from here, go down. And then we reach this equilibrium point. It's become the liquid phase. And keep going. Other points? So that means this happens, this phase transition happens, okay? And what about this point? What is the point corresponding to? As we mentioned, the Gibbs free energy is just the integration area beneath underneath this curve, right? Correct? And all the area underneath this curve positive, and this curve are negative, right? Then the phase transition point actually corresponding to the point which give equal area in these two parts. If we can find a line here, draw a line, straight line here, and then on this half, the area on this half and on this part equal to each other, okay? Then actually, it just gives us the equilibrium. Got my point?
What does that say over there? It says T equals something.
T equals to what? The constant.
Oh.
Constant. It's constant. The same here, okay? I'm sorry, I did not draw this picture very well, so actually it should be something like this. Okay? This area and this area should be equal to each other, okay? This area and this area should be equal to each other. That means we start with, this is A point, we start go to this point, and then we across this line. Okay, the pressure doesn't change anymore, but the pressure doesn't change anymore, the volume change. Okay, and you can see from this equation, because pressure doesn't change, the Gibbs free energy doesn't change anymore, right? That means at this point, the volume change, pressure doesn't change, the Gibbs free energy doesn't change. Go across this curve and to this area, right? And keep going. Okay, that's the phase transition. That's how the Van der Waals equation explains the phase transition, the compression of gas, and change the gas into liquid. Did I make myself understood? Okay. And there's something very interesting. Yeah. Sometimes, if you keep compress the gas, ideally, when we go to this phase transition point, basically this point, when these two areas equal to each other, the gas should be liquefied. Right? Should be liquefied into this branch. But sometimes it doesn't happen. Okay? Let me tell you. Right now, everybody knows it's very humid outside, right? And you can see the glass have water everywhere, right? If you go to the restaurant, if you stand out several times, the skin becomes wet. But you do not see the water flowing in the air, right? What's the reason for that? Because the water in the air right now is oversaturated. Okay, that means although the pressure low, the temperature is low and pressure is high, it still doesn't get solidified, liquefied. Okay, that means go to this area. It's it's keep going across, keep going along this line without being liquefied, until it's touch the moisture reach some objects. Okay, what's the reason for that? The reason is actually this liquefaction process doesn't happen spontaneously. It needs to have some nuclear site for the vapor to form into the droplet. Okay, if there's no nucleoside, this process doesn't happen spontaneously. That means even the pressure is high, temperature low, but it's still in the phase of the liquid, in the gas. Okay, that means right now we are in this state. It's not a stable state, right? But it still exists. So in that case, we call this state is the metastable state. Right? Metastable state. Yeah. It's called the metastable state.
Is it similar to super cold water?
Exactly. Super cold water, okay, it's metastable. Okay? It's not super stable, but metastable. If as long as you do not disturb it, it will there. Okay, it will be there. Okay. But if you keep moving, and reach the E point, then the curve should go to this direction. It becomes unstable, right? That means no matter whether you have the nuclear side or not, it's suddenly liquefied. Okay, it's suddenly liquefied. Okay. And in that case, actually you can see that we can further separate this one into two zones. Okay. We know this zone is definitely unstable. Okay. This area, we know that this area is unstable zone. Okay. This area is unstable. Okay. But in this area, this one is metastable. Okay. This one is metastable. These two parts are metastable. Okay. And this area is unstable. Okay. Got the points? And then, I don't know why, but the guy named one of us give the special name for the point of I and E. Okay, they call it I and E. It's called what? Spin knot. Okay, spin knot. Spin knot. I don't know what's the reason for that. What's the meaning of it? Okay, yeah, spin knot. Let's go back to this chart. That one only contains one curve, but for that one, we have several curves, okay? You can see this area is defined as unstable area, right? This area is unstable area, right? But we know that if we want to draw a line, give the constant volume across this, give the equivolume across this curve, actually boundary for the phase transition, or like we call it the spin node, actually is outside. This is spin node, this is spin node, okay? This is the unstable points. Actually, spin node is the outside this unstable area. So we have another zone. We have another zone. Okay? We have another zone. Okay? Inside is unstable state, and outside this is the metastable state. Okay? That means the phase transition can happen or not. Okay? If you have a nuclear site, the phase transition happens. But if you doesn't have, you have the super cold liquid, but super hot liquid, or super cold gas. Okay, you know what I'm saying? Have you ever tried to make the super hot liquid? You know how to make it? You know how to make a super hot liquid? You can try. Go back home. You want to know how to try how to make it?
Yeah, it was a pressure cooker.
Huh?
Pressure cooker.
What?
Pressure cooker.
No, not that complicated. Go to the supermarket. Huh?
Microwave DI water, right?
Yeah. Microwave the DI water. Okay? Buy the water, go to grocery, buy the pure water, okay, purified water, or deionized water. or distilled water. Do not use the mineral water, okay? Put it in the microwave, and put it in the microwave probably for about 1 or 2 minutes. Use the high power. Very carefully take it out. Okay, you find that the water is not boiling. But if you put something inside, it's starting to boil. Okay, do not injure yourself. Okay, I do not take any responsibility for any kind of personal injury when you perform this experiment. Okay.
Professor, we have DI water in research lab.
We have. And we also have microwave in the research lab.
Yeah.
Okay? But we do not have enough emergency packaging in the machine. Okay. Anyway, next semester, when we talk about phase transformation, I'm going to talk about another type of phase transformation. We call it the spinado phase transformation. So we will talk about this kind of behavior more, this kind of phenomenon in more details. Okay. Questions? Give me a second. Yeah, what's the question?
Why these two areas are equal? Is there any reason these two areas?
Why these two areas equal? The reason is like this. We know that when we do the integration, we have the curve looks like this, right? The curve looks like this. When we do the integration, go positive, negative, and positive again, right? We do positive, we do the integration on all these areas underneath, and we start to do all the area underneath, right? And then we start to remove. And when we got this point, give me a second, let me try to draw the picture better, give you a better explanation. We do the integration, basically we do the integration on all these areas. Right? We accumulate all this area, we start to reach this point, right? Yeah. And then when we do the integration along this line, we start to remove these areas. Right? We start to remove these areas. Right? If we do the integration, all this area underneath got removed, becomes negative, right? Correct, everybody? And then we, at this point, and then we reach this point, right? And then we start to add more area down here, right? So you can see that, yeah, and until we reach this point, right? So that means what? That means we need to find a place. Do that. Give me a second. Let me. Let me see. How can we draw it better? We need to find a point. This area, okay. And then we start to accumulate on this area. And this area. For example, like, yeah, we keep doing the integration, we get something here. Right, we got something here. So idea is, we need to find a state. We want to make sure the shaded area in this integration has the same area, the shaded region have the same area to the shaded region here. Understand what I'm saying? So if we do the integration to this point, that is to somewhere here, right? And if you keep doing, you move to this one and also remove this part. And then eventually you got something here, right? We want the shaded, both shaded area have the same area, right? Both shaded region have the same area. So we just need to remove this part to this part. Okay, that means this part and this part should have the same area than these two shaded areas. Understand what I'm saying? Did that make sense? Understood? All right, so basically, I think we cover all the information. Okay, anyway, so the conclusion is by considering the intermolecular interaction and the limited volume of the molecules, we can change the ideal gas equation to van der Waals equation and explain the phase transformation of the actual gas. Questions, comments? Questions, comments? Do you have a question?
If you really wanted to say something.
No. I mean, if you want to say something, you can say something. Okay. Homework. So I checked the homework. It seems like the most of the quantitative equation questions you do not have any problem. Most of the people get the full credit on it. Okay, but the discussion questions, there's some issue. I give you some explanation. Okay? The question 4. In class, we talked about for the reversible adiabatic process, we have the equation of the PV gamma equals to constant, right? And because of that, we know that two adiabatic curves doesn't cross each other. Now use the second law of the thermodynamics to explain why the adiabatic curve doesn't cross each other, okay? And the original design, let me tell you what my purpose, okay? What I want you to answer. But you can see that for different answers, I also give you the full credit. Okay, I find sometimes it's kind of smart, but it's not fully covered the knowledge, but still correct. And once again, if you do not receive full credit on a question, but you still believe that you give me the right answer, you can come to talk with me. We can discuss further. So if I agree with what you said, I can give the credit back, okay? My original design is like this. So if these two adiabatic curves cross each other, we can simply find another loop to connect these two curves, right? Then, for example, like the isothermal process, okay? Isothermal process. Okay? That means we can extract the heat from a single heat source and deliver work. This disobey the second law of thermodynamics. That's it. And I find that some argument looks like this. I find some student who will give me this argument, okay? Because this, for example, the student told me that because this is one adiabatic process, this is another adiabatic process, for example, like this one, and both adiabatic process in principle should have delta S equals 0. Correct? Then his argument, her argument is like this. Then this point and this point should have the same entropy. Okay? That means two different states have the same entropy. This obeys second law of thermodynamics. And I remove some credit from it. The reason is, yes, the entropy is a state parameter or thermodynamic parameter, right? But we never say that two different states cannot have the same entropy, okay? We can only say that one state cannot have two different values of entropy. But we never say that two different states can have the same entropy. Understand something? So that's wrong, okay? So if some of that second law, some of that doesn't tell you that these two different states cannot have the same entropy. Yes, it can, why not, right? I'm a different person, we are different from each other, but we can share the same name. No problem, right? But for me, I cannot have two names. You know what I'm saying? This is the main issue I find identified in this problem. But the good thing is, I have no idea why this answer is given by ChatGPT or Gemini. But I hope not. But if not, that's a good sign that you do not rely on AI. Although you made a mistake, that's fine. Okay. What's your question?
I didn't get a grade back. Are you done grading everything?
I will only calculate the final score before the end of semester.
Everybody got emails. I didn't get an email.
You did not get an email
Yeah.
for the homework?
Yeah.
Can you resend me the homework? I can grade it, okay?
Yeah. You want me to email it to you though?
Yeah. Just email to me. If you do not receive my feedback on your homework, just send me the reminder, okay? I will grade it, okay? I think most of people already got it. You didn't get it?
I didn't get it.
Oh, really?
We submitted it
I
to
sent it when
Canvas.
Oh, I told you, if you send it to Canvas, sometimes it's give me the reminder, sometimes doesn't.
So do you still want us to resend it?
Send me through the email.
Okay.
Okay, send me through. That's the reason I really hate Canvas, you know what I'm saying? Some students send me through the Canvas. I received the message, but somebody I did not.
So do you want Canvas or do you want Outlook email?
Outlook,
Okay.
Outlook, okay? And to make your job easier, I don't know whether it makes your job easier or not. For the in-class student, can you give me the hard copy? If you want, you can also give me the hard copy. You do not need to scan it, okay? If you want to give me the hard copy, also work, okay? But for online student, I think they can just give me the e-copy.
Actually, I now see it. I thought that was a response for that to receive it.
Oh, no.
No, I got it. Yeah.
You got it?
Yeah.
Oh, by the way, for most of your email, I just put FYI for interest, okay? It doesn't mean I disrespect your homework. I'm so lazy don't want to say any word because I have so many students, I don't want to type one by one, okay? I just put FIU, okay? But I really like you guys, okay? I really respect your work, okay? It doesn't mean I disrespect your work, okay? You just like save some time, okay? But if,
You can finish what you're saying. Sorry.
yeah, but for some students, I put more words because I'm not sure about what he's talking about. I'm probably made some mistake when grading. So if I have a comment, probably can respond to my message, okay? And for the full score student, I just put well done, okay? Probably I should put well done with ChatGPT or whatever, but anyway, I hope this is from your own. Okay. But the other thing is that although I write FYI for interest in my message to save time, but I still suggest that you do not write this one to your future boss, okay? You still want to put his name and proper subject line there. Anyway, so the second question. Practice 8. So I ask you to calculate the entropy change of a straight bar, okay? We have the temperature gradient of the straight bar from T1 to T2, okay? From T1 to T2. So there's not quite a lot of there are not quite a lot of issues. There are not quite a lot of the difficulty to understand the physical process, but actually it's kind of like mathematical properties. So to calculate the entropy at the beginning, so it's T1, T2, and the final temperature, as you can see, is the everywhere have share the same temperature is the T1 plus T2 divided by 2. Okay? But we need to calculate the entropy change of each part, okay? Because the temperature change are different. Okay, for example, in the middle, simply there's no temperature change. But on both ends, the temperature change the most. Okay? So what you need to do is you need to know the temperature distribution at the beginning, okay? So for example, Tx equals to T1 plus T2 minus T1 divided by L times X, okay? Okay? And the entropy change, you already know that, okay? So what you need to do is the capacity times dm, that means the mass of the small portion of it, okay? And then is what? Ln half T1, T2, and Tx, okay? Got points? Okay? And of course, the dm is the intensity times x, okay? And in order to calculate the entropy of the entire bar, you just do the integration, okay? This part is a little bit tricky, a little bit difficult, but you can do the job, okay? I think, do you know how to do this integration? Ln x dx. Do you know how to do this integration? Ln x dx. We know that the 1 over x, this one is ln x, right? But do you know how to do this integration? If you know how to do that, I'll explain. Okay? Okay.
You 1 over.
Huh?
You do will go UV formula?
Huh?
UVdx formula.
What do you mean?
That means x to the power 0 into this.
No, no,
Yeah,
it's
the
from the
equation
left
of
hand
L
side.
of X is just
Yeah, yeah,
one
it's
word,
from
so
0
just
to
pull it
L.
out.
It's from 0 to L. But what I'm asking is that, do you know how to do this integration? Ln x dx. Okay, if you know that, I'll explain. Okay, that's the solution. And a lot of students, they only give me this one. Okay, finish your job. Okay, finish your job. I remove 1 point. Okay. It's just like in the future, your boss asks you, "Hey, you need to do some calculation for me," and your response is check with the ChatGPT. What's the use? You cannot do that. Okay, finish your job.
Could you do that intro? I don't have a strong math background. Would you mind doing the intro real quick? Line, I mean, I can look it up later.
You want
The whole thing, the CPU.
You want to challenge me?
CPU row.
Okay, I will show you. I will show you. I will show you.
Consider, or just, am I being lazy?
I will show you.
Okay.
I only show you how to do the integration about this part. I mean, we only need to do this one, right? We only need to do this integration, right? So this is what? For the other part, it's just constant, right? Wait. No. I mean, you only need to do this one. Basically, you only need to do this one, right? What's that? Something like this, right?
Mine.
Oh, my, huh?
Minus?
Minus? Three minus. I think it's, yeah. I forget about minus. You can add a minus on yourself.
Oh,
This one just like alpha plus beta. Yes. Correct? We just choose this one as beta T1. We just make constant, make it simpler, right? And then this one equals to 1 over alpha. And this one is changing from the original from 0 to L. Right now it's from beta to L alpha plus beta. Right?
And
Correct?
so for the longer one, the CP and the density and all that, so they can just take
Well,
it out.
that's
of
just
coefficient?
constant.
Oh,
Just
okay.
constant. We just take it out.
I was
right?
doing like the formula. I
Right.
did.
And then you can do this calculation. So in order to calculate this integration, ln x dx, so basically you need to do something like this. This one equals to ln x times x minus x d ln x, right? And this one equals to ln x dx minus this one equals to x times 1 over x times dx. Okay, let's cancel each other. Basically, this one is Lx dot x minus x. Okay? And then you put the upper limit and lower limit. You got the conclusion.
Thank you.
No problem. Good evaluation. Okay, what's the time right now?
111.
We still have 4 minutes. Okay, last 2 questions. Last 2 questions. When is your qualified exam? Is that possible for us to fabricate a single direction mirror with its fully transparent on one side but fully reflective on the other side? Use a thermodynamic principle to analyze the question. So the answer is no. Everybody knows it's no. Okay? But what's the reason for that? The reason is, I mean, roughly you're right, okay? Basically, if we have this kind of mirror, that means we can spontaneously make the heat, separate the heat. That means originally we have 2 parts have the same temperature, but seems like it's only a lot light go from one side to the other. Then the heat will spontaneously transfer from one part to the other. That means the cooler part become even cooler, the cold part, the hot part become even hotter. Okay, this is the second law of thermodynamics. Okay. Then somebody asked me a question. That if you see the video, you see the movie, you see the FBI trying to ask questions, and then some 2 bodies just sitting, supervisor sitting at the door. And they can see through the glass, but the other person inside the room cannot see outside. What's the reason for that? The reason is the difference in the light intensity, okay? You can see that the super red always in a very dark room, okay? And the people who enter investigation always in a very bright room, okay? So it's the same thing. If you go outside, you cannot see what's happening inside the glass, okay? You cannot see what's happening in the office because the sunlight is so strong, okay? But that doesn't mean the glass only allow light to go from one direction to the other instead of the other way, okay? But you can see that inside the room, you can see what happened outside very clearly. But the outside people cannot see you, right? But in the night, it's the opposite way, okay? You go outside, you can see what's happening in the office very clearly. But in the office, you cannot see what's happening outside, okay? The same piece of glass, just because the intensity of light, the illumination is different, okay? That's different. But there's one thing you should be very careful. Go back home and check, okay? We call it the Faraday effect. Basically, by using this kind of effect, we can make the optical diode. Optical diode. It's allow light to pass through one direction. Okay? Check online, we have this kind, we call it the Faraday. Just go online, we call this kind of atom, we call it the Faraday light, Faraday isolator. Okay? Basically, it's a piece of the device. We have some glass in the middle, and the laser can only go through from this direction to this, can only go this way, but you cannot go this way. Okay? Check online and try to understand why this kind of device exists, and why this device disobeys the second law of thermodynamics. Open question.
That's like diodes in circuit.
No. It's just for the diode in optics. Allow light to propagate along one direction, not the other way. Okay? Check online what's the reason for that.
Can you explain number 10?
Huh?
Can you explain number 10?
There is one device, optical device. We call it the Faraday isolator. The Faraday isolator is kind of like the cylindrical structure. For example, this is the Faraday director, okay, the oscillator. We have a laser light. If you put the laser from this direction, it will exist from the other port. If you shoot the laser from this direction, it doesn't come out on this way. That means it's only allowed the laser propagate along this direction, not the other way. Okay? What's the reason for that? And why this disobeys the second law of thermodynamics? Okay? Check online and you try to understand this question. Just ask ChatGPT, can give you an answer. Last question. So whether we can put, if we put a single convex lens in the furnace, whether we can focus radiation to a hot spot? The answer is no. The same thing. So if this is a hot spot, this is T1, this is T2, okay? That means we can create a hotter spot inside a single hot sauce, okay? You know what I'm saying? And the heat flow is from low temperature to the high temperature. This disobeys second law. And another explanation can be like this. So that means if this happens, we can create a hotter heat source inside a low temperature heat source. And based on these two heat sources, we can build up the cycle. We can build up a thermodynamic cycle, okay, and deliver work out. Okay, if we treat this one as a black box, we don't know what's happening, but we know that right now we can extract energy from a single heat source and deliver and perform the work. Okay, this is the second law of thermodynamics. Okay, and for some students, I remove some credit. He's saying something like this. No. He said no. Okay, he said no. Because T2 has a higher temperature than T1, and the heat flow from T1 to T2. Okay, and then from thermodynamic law, second law of thermodynamics, the heat cannot spontaneously flow from low temperature heat source to a high temperature heat source. Actually, second law thermodynamics doesn't tell you that. Okay, the heat can spontaneously flow from low temperature to high temperature. Okay? It can happen, okay? Let me give you an example. For example, we have the high temperature heat source. We have a low temperature heat source. Okay, then we do some work. Okay, we can use this work to pump the heat from the T2 to even higher temperatures. Can we do that? Yes, we can do that. Okay, we can do that. Okay. That means if we treat this one as a black box, we know that there's some heat transfer from T1 to T3, and it's a spontaneous process. Okay? How do you make this argument correct? That means we only have one heat source. We only have two heat sources. One is high temperature, the other is low temperature. Then it does spontaneous happen. Okay? But if you have three, yes, you can. Okay? You need to specify you only have two heat sources. Okay? All right, I think that's answered all the questions. I can disclose this is one question in your qualified exam.
What if you had some type of like, they have heat energy, the thermoelectric device that could take waste heat.
Come.
Yeah, I'm gonna come, I'm interested in.
Yeah. Think about it now. Think about it. So you have the solar cell. Okay? Solar cell